Hello, grab your calculator and follow along as I discuss the rules of equilibrium. There are three simple rules, and this is very easy to understand once we get through the whole video, you'll see. So first of all, there are three rules. You can flip a reaction, so A going to B, we can change it, B going to A, and we use what's called the inverse rule to calculate the equilibrium constant. We can also combine two separate reactions, and maybe we have the equilibrium constant of one and the equilibrium constant of the other. We can use the product rule to calculate the equilibrium constant of the combined chemical reaction equilibrium. And the third thing is we can modify coefficients, and we use what's called the power rule for that, okay? So let's go ahead and show how this works. Let's say we have a reaction. A is in equilibrium with B, and the equilibrium constant happens to be 50. Now we know that KEQ is B over A. It's products over reactants. So then, if we take the reaction and we flip it, I call this flipping. If we instead write A to B going B in equilibrium with A, the equilibrium reaction is 1/50th. So to calculate the inverse, you just do 1 divided by 50 and you get some number on your calculator, okay? And why is that? Well, it's easy here to explain how that works. The equilibrium constant is products over reactants. A over B is flipped compared to B over A. So that's why instead of 50, you have 1 over 50, all right? Now here's an example. We have this chemical reaction here. It looks kind of complicated, and the equilibrium constant is, very small, 2.99 times 10 to the minus 7th. Remember, for a small equilibrium constant, the reactants are heavily favored, okay? You have many, many reactants, very few products. All right, so what do we need to do? First, we want to write out the equilibrium reaction reverse. So you just flip everything, okay? And that's all. Keep the balanced chemical equation the same. Now, in step 2, we want to calculate 1 over the Kc value. So this is where you want to grab your calculator and see if you get the same number I get on my calculator. So here, I do 1 divided by that number, and I get 3.34 times 10 to the 6th, okay? So that's how you do it. You just do 1 divided by the number if you're flipping a chemical reaction. All right? Here's a practice problem for you. We have acetic acid in equilibrium with H plus and C2H3O2 minus. The equilibrium constant is 1.8 times 10 to the minus 5. What is the equilibrium constant for this chemical reaction? You can see how it's flipped. All right? So that's for you to try on your own. All right, let's talk about combining reactions. So this is rule number 2, okay? So we have reaction 1 there written, and we have reaction 2 there written, and we have equilibrium constants for these two different reactions, okay? So what you want to do is add these two chemical equations together, much like you would add two mathematical equations together, okay? So all the left-hand side stuff goes on the left of the equilibrium arrow. Make sure you keep the 2 for the coefficient of C. All the right-hand stuff stays as a product on the total equilibrium reaction. Now, when you write a combined reaction, you always want to check for similar terms on either side of the chemical equilibrium. Here we can see that there is C written on the left and on the right, so we can subtract 1C from both sides of the chemical equilibrium to simplify it a bit. And so the final, I forgot the state here on C, I'm sorry, but we have A gas plus C gas in equilibrium with D gas plus E gas. Now, how do we calculate the equilibrium constant for this crazy combined reaction? Well, we use what's called the product rule. We multiply the two equilibria that we have for reactions 1 and 2. 25 times 100 is 2,500, okay? So easy math, but double check, I make mistakes. All right, here's an example, a little bit more complicated, but actually we use this when we talk about formation constants and precipitation reactions, for example. So we have reaction 1, this crazy long thing, and the equilibrium constant is, 10 to the minus 19, that's pretty small. And then we have reaction 2, that huge long thing, and the equilibrium constant is, wow, that's big, 10 to the 18th, okay? And we want to know what is the equilibrium constant for the combined chemical reaction. So here we go, make a long addition bar there, and you want to add, and remember, I'm just going to kind of skip a step here, but what we see is that copper 2 ion is on the right of reaction 1, and copper 2 ion is on the left of reaction 2. So those are going to cancel out. There's a coefficient of 1 not shown there, but those perfectly cancel out. So when you add all these things up, you want copper hydroxide on the left, okay? There's 4 ammonia molecules on the left. Now we have an equilibrium arrow, and then we have all the right-hand stuff. Remember, copper ion has canceled out. We have copper tetraammonium complex ion, okay? And we have 2 hydroxide ions. So that's it. That's the net thing when you cancel out the copper ions, okay? Keep your coefficients, keep all the stuff on the left still on the left, and just try to be organized when you do this. Now what we want to do is use the product rule to calculate the value of the equilibrium constant for this combined reaction. So again, use your calculator and check what I get here. Whoa, I got 1 on a TI-37 calculator. That can't be right. So let me check on this better calculator, which is a Casio. 1.6 exponent 19 minus times 6.25 exponent 18. And I get 1 as well, okay? So, this is kind of rounding off the math, and it comes out to be 1, all right? If you were to write this on a test or something, I would write 1.0, which has 2 sig figs, and so I don't know how many digits should be there. This calculator is doing a little bit of rounding, and it's struggling with the math, okay? So anyway, that's how you do this. The number, it's 1.0 on these very basic calculators that we have, all right? All right. Let's talk about rule 3. This is the power rule, if you remember. So let's say we have a chemical reaction, A in equilibrium with B, and the K for this reaction is, I don't know, 5, okay? Now let's say we wanted, for some weird reason, to multiply that whole equation by 2. So we have the whole chemical reaction, and we're going to multiply every single coefficient by 2. So now we're going to have 2A of a gas in equilibrium with 2B, which is gas, okay? So what is the equilibrium constant for this? We just square the value of our equilibrium constant because we multiplied by 2, okay? So if you multiply all the coefficients by 2, you're going to square or use a 2 power on the equilibrium constant to get 25, all right? So the OpenStax textbook explains more about almost like a mathematical proof, how is it squared, okay? I'm not going to go into that. Just memorize, if you multiply by 2, you're going to square. If you multiply by 4, you're going to do the power of 4, and so on, okay? All right, so here's an example. We've got, once again, ammonia synthesis. The equilibrium constant is 5.3 times 10 to the minus 5. And we want to know what is the equilibrium constant for this reaction. So when you look at this reaction, you want to see, hey, how are the coefficients changing? Every single coefficient looks like it's being tripled, okay? We have 1 nitrogen, then we have 3. We have 3 hydrogens, then we have 9. We have 2 ammonias, now we have 6. So everything's being multiplied by 3. So if we want to calculate the equilibrium constant, we need to cube the given value to us, 5.3 times 10 to the minus 5. Check on your calculator to see if I've made a mistake in the video, but I've got 1.5 times 10 to the minus 13. So that's the equilibrium constant for this, all right? So here's a problem that you actually might encounter. Oftentimes these problems you'll have to use 1 or 2 or even all 3 rules to solve the riddle. So here's a problem, I think, from our OpenStax chemistry textbook. It's from McGraw-Hill. So given the following reactions and their equilibrium constants, blah, 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 K is 1.6, blah, 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 K is 0.67, calculate K for this chemical reaction. Iron plus water goes to iron 2 oxide plus hydrogen gas. Where did the CO and CO2 go? Gosh, what do we do? Okay, let me take you through this stepwise. Look for the positions of reactants and products, okay? So first, let's look at water on this reaction 1. Water's on the left, water's on the left. Okay. We have hydrogen on the right, and we have hydrogen on the right. So everything is positioned correctly, and so I'm putting a check mark, meaning that I'm not going to have to flip this chemical reaction, okay? Let's look at the next chemical reaction. Reaction 2, iron 2 oxides on the left, but iron 2 oxides on the right. And then we look at iron solid. Iron solids on the right of reaction 2, and iron solids on the left of reaction 1. Okay. Now, I want to make a note. Some people get confused by the solids. They remember, wait a minute, I thought solids weren't supposed to be in the equilibrium expressions. Yes, that's correct, but it's part of the balanced chemical equation, so you need to include it in there, okay? So it looks like this reaction's been flipped, all right? So what we need to do is take that chemical reaction there and flip it and change the value of the K so that we have the correct value for the flipped equilibrium constant, okay? So take this chemical reaction, flip it around by reversing the reactants and products, and then remember to use the inverse rule. So take 1 divided by 0.67, and you get 1.5 as an answer there, okay? So I'm going to write that down. I'm going to put a check mark there because the left stuff is on the left and the right stuff is on the right. All right, the next thing you want to do is look at coefficients, okay? Step 3 is to look at coefficients. Sometimes you have a 2 appearing and it's like, wait a minute, I don't have a 2 anywhere. Here, everything's 1, so yes, we skip this step. It's a very, it's a simpler problem, okay? Now, what do we do next? We add these reactions together. I've highlighted in green how the carbon monoxide cancels out when you add these two together, and I've highlighted in red how the carbon dioxide cancels out when you add these two together, and lo and behold, you get exactly the reaction that they've given us in the word problem to calculate the K for, okay? How do we calculate the K here? Sorry, the number's off the screen there behind my little image there, but grab your calculator. We use the product rule, so 1.6 times 1.5, I get this number on my calculator, okay? Please, as always, follow along if I make a mistake or so, okay? Here's a practice problem for you, all right? So you have to decide, do I flip something? Do I multiply an equation by 2 or add the two equations together? Or how do I get this final equation to match, okay? So I look forward to seeing if you're able to solve this problem. All right, these are the summary of rules. So the inverse rule, remember, you just divide 1 over K. That's how you do it. For the product rule, you multiply the two equilibria, and then for the third rule, we use the power rule. So if you're multiplying by 2, it's going to be K to the second power. If you multiply by 3, it's going to be K to the third power, okay? Thanks for watching. Please like, please consider subscribing, and have a great day, everybody.